The rules that we've talked about for drawing Lewis structures so far are an excellent starting place. And essentially what we're doing, just to remind you, is we're not really trying to figure out the structure of the molecule, but we're trying to represent the electrons, specifically the valence electrons, and the bonding structure, essentially, of what's going on in a covalent species. Who's bonded to whom? Is the bond a bond order 1, 2, or 3? That sort of arrangement of the electrons, and we're going to build on that in the next series of videos. But right now what we want to talk about is we want to talk about tweaking the structure, because what we come up based on those rules, what we come up with based on those rules does not always give us something that matches what we see in the laboratory. And a prime example is looking at H2SO4. This is if you dissolve it in water, it is sulfuric acid. If you don't dissolve it in water, this molecule is referred to as the hydrogen sulfate molecule. This is the sulfate ion. And the Lewis structure, we begin by drawing the skeleton. And the first atom listed is the center, and everybody else is attached, unless the first atom is hydrogen, in which case the second atom listed is the center, and everybody else is attached. Now, when we have these oxyacids, these molecules that when dissolved in water are acids, that contain oxygen, we see a particular arrangement of the skeleton, and that is that the hydrogens that cause them to be acidic, cause these molecules to be acidic, are attached to oxygens, one hydrogen for each oxygen. So as I draw this skeleton, I'll go ahead and put the 4 oxygens around the sulfur, but the 2 hydrogens will be attached to 2 different oxygens, and it doesn't matter which oxygens I attach them to. I'll put them to these 2. You could put them up and down and left and right, and that part doesn't matter. So this is the skeleton for H2SO4. Now I'm going to add up my valence electrons. All right, you should be getting good at that. And so this structure will have 32 electrons when I'm finished. Step number 3. Remember that we have already added some electrons, but we will begin by adding lone pairs of the remaining electrons to the outside atoms. In this case, this will be the oxygens. Hydrogen doesn't want any more than the 2 it already has as part of this bond. So start adding them to the outside atoms and work our way towards sulfur. Just to note, sulfur could have an expanded octet if we needed it to. He is in the 3rd row. Remember, the 3rd row or lower. All of these have empty d orbitals on their valence level. Sulfur doesn't have any electrons in his 3d orbitals, so he could add some there if he needs to. But according to our page of rules, we only need to add extra electrons to sulfur. We only need to expand his octet if we have remaining electrons once we've added our electrons to the outside atoms in pairs. So here we go. Let's count by 2s. 2, 4, 6, 8, 10, 12 have already been added. 14, 16, 18, 32. Putting in the last set of electrons around my outside atoms in lone pairs gets to my 32 electrons. At this point, everybody has an octet, including the central atom, the sulfur. And so at this point, according to the rules, I would stop. This is the Lewis structure. However, if we take this molecule into the laboratory and study it, we would expect to see each of these sulfur-oxygen bonds to have a bond order of 1, because they're all single bonds, which means each of these sulfur-oxygen bonds should be approximately equivalent in length and strength. And that is absolutely not what we see. What we see when we take this into the laboratory looks like these oxygens that do not have a hydrogen attached are sharing an additional pair of electrons. It looks like the 32 electrons are arranged in this fashion. Now notice we did say sulfur could have an expanded octet, and that's what we've done. But how in the heck are we supposed to know he needs to have an expanded octet here? Should we just willy-nilly expand octets if we can? And the answer is no. You should never willy-nilly do anything for chemistry. especially in the lab. But anyway, how do we know this? Well, we know this by analyzing or tweaking the Lewis structure a little bit using the concept of formal charges. We've looked at a lot of charges in chemistry so far. We have honest-to-goodness charges. A proton is positively charged, an electron is negatively charged. We have charges on atoms. We call these ions. We have cations and anions, and they're charged because they either have extra electrons or they're missing electrons. We have charges on polyatomic ions, a group of atoms that have a charge. We have charges that are counted as oxidation numbers as we look at electrons gained or lost during a chemical reaction. We had partial charges earlier in this module, and now we have another type of charge. These are called formal charges, and they are imaginary. They are a bookkeeping method of keeping track of electrons in a Lewis structure to help us decide what is the best Lewis structure, to help us tweak the Lewis structure to find the best one. All right, this is a step further than the general rules, and we have to analyze formal charges in order to do it. So let's talk about what formal charges are. I'm going to draw a very simple Lewis structure. This is the Lewis structure for water, H2O. Let's use it to learn how to write formal charges. We're going to count formal charges. You count them for each atom. So for example, the formal charge on this hydrogen is calculated. Formal charge on hydrogen is calculated by starting with how many valence electrons does hydrogen have. Hydrogen has 1 valence electron. Then you subtract the number of electrons that belong to the hydrogen in this particular Lewis structure. So hydrogen's formal charge might change depending on his Lewis structure. Well, in this particular Lewis structure, hydrogen has a single bond that he's sharing with oxygen, and so the rule is that we count, remember a single bond is 2 electrons, let me draw the 2 dots. We count one of the dots, one of the electrons for the hydrogen, and we'll count the other dot, the other electron for the oxygen. Now this is not what we do when we count our octets. This is a different procedure. For formal charges, we will only count one of these electrons in the bond, and that's what we subtract from the number of valence electrons. So we start with the valence electrons, we subtract off the number of electrons that belong to the atom in the structure, the number of valence electrons that belong to the atom in the structure, and that calculates our formal charge. The formal charge for hydrogen is 0. Notice that this right-hand hydrogen looks exactly like the left-hand hydrogen in terms of his Lewis structure. He comes in with 1 valence electron. He has 1 electron in this structure. His formal charge is also 0. For oxygen, in this particular structure, oxygen has 2 lone pairs and 2 single bonds. So if we were to calculate the formal charge of that oxygen, we would start with his number of valence electrons, that would be 6, and we would subtract the number of electrons that belong to oxygen in this structure. A lone pair belongs to the atom that the lone pair is on. So there are 2 electrons that belong to the oxygen. Here are 2 more that belong to the oxygen, and 1 of each of the single bonds belongs to him. So 2, 4, 5, 6, his formal charge is also 0. We do see a lot of zeros because 0 is a very stable formal charge, but it's not always a formal charge of 0. Let's do another example. All right, I'm going to draw the Lewis structure for SO2. I'm going to draw it kind of quickly using our rules because I know you're getting good at it, but we have a sulfur and 2 oxygens, so here's my skeleton. All right, we end up with this Lewis structure by step number 3, filling up our outsides octets and then moving to our inside. And you'll notice that the sulfur does not have an octet, and so I will take 2 electrons from any of the outside atoms and make them share. So this is the Lewis structure for SO2. Since I have drawn a double bond, I want to check for resonance, and indeed there was an equivalent place I could have put the double bond, so I will draw resonance structures. The resonance structure looks exactly like this in terms of the skeleton, but it has the double bond in the other position. And then I would fill in my lone pairs. Notice that this oxygen is only going to need 2 lone pairs because he has the double bond, and this oxygen will need 3 lone pairs. So there are my 2 resonance structures for SO2, and I can assign formal charges. Now typically if we're assigning formal charges, we'll just look at one of the resonance structures to assign them. So let's look at this top resonance structure and assign formal charges. The formal charge for the oxygen, now notice my 2 oxygens do not look exactly the same, so let's start with this left oxygen. The formal charge on the left oxygen starts at 6, because that's the number of valence electrons that oxygen has, minus the number of electrons that belong to it. 2, 4 for the lone pairs, 5, 6 for the double bond, 1 for each of the bonds. Remember, a double bond has 4 electrons or 2 pairs of electrons. Half go with the oxygen, half will go with the sulfur in terms of counting formal charges. Remember, we count them all when we get our octet, but we split them in half for formal charges. So the formal charge on the left oxygen is 0. Now the formal charge on the sulfur is the number of valence electrons on sulfur, so 6 minus the number of electrons that belong to it. 2, 3 for the single bond, 4, 5 for the double bond. 6 minus 5 is a 1. It is a positive 1. Formal charges do have charges, and so the formal charge on sulfur is a +1. Typically we circle the formal charge. You can put them above the symbol, below the symbol, to the side of the symbol. That doesn't matter, but the notation is typically that we circle them. The only time we don't circle them is if the formal charge is 0, because it's already a circle. And just as a note, remember, for ionic charges we usually write the number then the sign. For oxidation numbers we write the sign then the number and put it in parentheses. For formal charges you write the sign and then the number and circle it. All right, one more. Formal charge for the right-hand oxygen. Let's do this in green. So the formal charge on this oxygen is equal to 6 minus, because oxygen has 6 valence electrons, 2, 4, 6, 7. 6 minus 7 is -1. The formal charge on this oxygen is -1. If I add all the formal charges in a structure, I should equal 0 if it is neutral, or the charge if it is an ion. If I'm drawing the Lewis structure of a polyatomic ion, all the formal charges will add together to give me the charge on the polyatomic ion. This is very similar to what we saw with oxidation numbers. +1, -1, 0. Add these together, I get 0 because this is neutral. That's how I assign formal charges. Now, how do I use them? Let's go back to our original example. In our original example, we said that what we see in the laboratory looks more like this than what we came up with first. So let me put that back up here. All right, this was the structure that we came up with using the rules. If we look at formal charges in this structure, notice that these 2 oxygens are going to have the same formal charge. So the formal charge on these oxygens is equal to 6 minus 2, 4, 6, 7, or -1. These 2 oxygens have a formal charge of -1. These 2 oxygens also look similar. So the formal charge on the oxygens in blue will be 6 minus 2, 4, 5, 6, or 0. Hydrogens are very easy to do. Hydrogen has 1 valence electron and 1 in its bond, so we almost always see hydrogen with a formal charge of 0. And now let's look at our sulfur. The formal charge of this sulfur is equal to 6 minus 1, 2, 3, 4, or a +2. So I've assigned all of my formal charges. Let's look at the formal charges in the top structure. In the top structure, every single oxygen is going to have the exact same formal charge because every single oxygen has 2 lone pairs and 2 bonds. This oxygen has 2 single bonds, this oxygen has a double bond, but I count the formal charges exactly the same. So the formal charges for the oxygens in this top structure, 2, 4, 5, 6, 0. Every single time it's 0, and you can double check that. Hydrogen is again 0. And what is the formal charge on our sulfur? 6 minus 1, 2, 3, 4, 5, 6, 0. Now in the bottom example, in the bottom structure, all of our formal charges do add together to give me 0. Plus 2, minus 1, plus 0, plus 0, plus 0, plus 0. They all add together to give me 0, which they have to if I've assigned them correctly. In the top one, they are all 0. So they all add together to give me 0. And again, they will if I've assigned them correctly. But there is something about this top structure that is better than the bottom structure. The bottom structure is not as good a structure as the top one because it doesn't match what we actually see in the laboratory. And so we explain it by saying that the formal charges are happier, that it is more energetically favorable, it is more stable because the formal charges are all 0. So for formal charges, best is closest to 0. Now they don't all have to be 0 to be the correct Lewis structure, but the closer they all are to 0, the better the Lewis structure is. In addition, if I do end up needing negative formal charges like we did down here with oxygen, the negative formal charges are happier. The negative formal charges are happier on the more electronegative atom. Recall from our discussion on electronegativity, fluorine is the most electronegative, oxygen is second, nitrogen is third, chlorine is fourth. So if there has to be a negative formal charge, it is more stable if it is on the more electronegative atom. And lastly, if you have big positives and big negatives, you don't want them next to each other. You want them not next to each other. So having a +2 next to a -1, although that's not terribly big, but positive and negative formal charges next to each other aren't as stable, especially the bigger they get. Because again, closer to 0 is better, and you do sometimes need pluses and minuses, but if they are next to each other, that's not as good as if you can get them where they're not next to each other. I suggest that you look at examples in your textbook about picking a best structure based on formal charges and see if they make sense to you.